Could you record it for me? Because I'm on
Yeah,
my phone.
I think I got a recording now.
Perfect. All right, yeah, brother man. So whenever you're ready, go ahead, work your magic.
Yeah, let me just here. There we go. Cool. So yeah, today I'm going to talk a little bit about planets. It also will diverge a touch into astrobiology and the search for extraterrestrial life at the end, because those questions kind of naturally arise from talking about planets that orbit other stars. I specifically kind of want to answer these questions of what they are, how they are, and why we care so much about them. And the thing you're actually looking at right now is something I'll talk about a little later. It's called a direct observation. And that's actually an observation of another star. That's kind of what that dark thing in the center is. We block out the stars so we can see the planets around them with 4 planets orbiting it there. So I'll get into kind of, oh, there's kind of 2 answers to the question, what is a planet? The first one I'll give you is like the quote unquote scientific answer, which is that it's any object that orbits a star that is large enough to make itself into a sphere. So it has enough mass that gravity pulls it into a spherical shape. It's heavy enough to clear any other object out of its path. That's ignoring like moons that it ends up capturing in orbit. And then also it's orbiting in a fairly circular path, not super elliptical. And that's kind of the weakest of the 3 requirements that people normally list, because as we learn a little bit, planets don't orbit perfectly circular. They have what's called an elliptical orbit, which is kind of slightly compressed and ellipse shaped. I try to give a better answer because I don't love that answer, since there are some technicalities and some stars that look a lot like planets and some planets that look a lot like stars. So the goal of planetary science is to kind of answer that question. It's to answer what do we want to define as a planet and what do we want to define as not a planet. There's also no strong single definition of the word planet. If you look at the planet we're on, it's obviously very, very different from something like Jupiter, which is similarly different from something like Mercury. So the conditions of your formation and this kind of way your planet exists influences what it looks like a lot and doesn't necessarily fit a good definition, but generally it's a spherical object locked in orbit around a star that we wouldn't call a star. I will now move on to the natural question that comes out of defining planets, which is what to do with Pluto. There's kind of 2 sides to this debate. I try to fall on the side of Neil deGrasse Tyson, but I can see the reasons why people disagree with that. And to be clear, what happened was he didn't decide Pluto wasn't a planet. He decided that in his planetarium it would be listed as a dwarf planet. So kind of the arguments for it being a planet is that if we call it a dwarf planet, it's still considered a class of planet. It looks a lot like some of the other planets in our solar system, albeit much smaller and further out. And we've kind of always classified it as one. It got lucky in that we observed it pretty early on in our understanding of how solar systems work. And so we just shuffled it into the same category of every other object we observed that moved in ways we couldn't really explain. The other side of the argument is that Neil deGrasse Tyson, the science man, kind of defined it as a dwarf planet, not a planet. It doesn't quite fit those requirements I talked about at the beginning. It's made itself a sphere, but its orbit is not very circular. It's sometimes closer and sometimes much further away. And it also happens to not, if all the other planets orbit on this plane, which they do, Pluto kind of has this big angle that it orbits on. And then the last thing is that it hasn't really cleared its own path out of all other objects. There are some stuff that intersect it in orbit and stuff that kind of just exists in its path. So it is kind of a lively debate, and it's just a matter of definition more than a matter of what Pluto is physically. So I'll give a quick run through of what's kind of around us. You probably know a lot of these things. A couple of them are a little bit more specific knowledge. So we have 8 planets. I will now make a statement that Pluto is not a planet. 4 terrestrial ones that exist near the sun, and that is Mercury, Venus, Earth, and Mars. And those are characterized by having large rocky centers with relatively small gaseous atmospheres. Outside of that, well, between Earth and Mars, we see our first belt of asteroids called the asteroid belt. They're things that are too small to be considered planets. It's kind of just this field of more asteroids than everywhere else. It's not like what you see in movies where you're trying to fly your spaceship through and you're running into asteroids all over the place. It's far less dense than that, but it's more dense than anything else in our solar system. Outside of Mars then are the four gas giants. They're far away, and that is because of some things that go on in the formation that I kind of hit on a little bit later. Those are Jupiter, Saturn, Uranus, and Neptune. They're characterized by being mostly gas with rocky or icy cores in the center, but they typically are when you think of Jupiter, just gas all the way down, getting denser and denser. Then outside of those, we have another belt. It's called the Kuiper belt. It holds kind of this cluster, again, not a cluster, but higher level of number of asteroids than we expect. Pluto is typically considered a Kuiper belt object. That's why it isn't considered a planet necessarily. And then way out, there's a bunch of other stuff. It's called the Oort cloud. Again, these are more planetesimals, small planet-like things, asteroids, comets, things like that. These you typically can't observe with the naked eye. You would need kind of high-powered telescopes to see them. There are two general types of planets, terrestrial and gas. As I kind of went through before, terrestrial planets have large rock masses, small atmospheres. They form from kind of the dense metals that get trapped near a star. And one interesting thing that you learn when you start astronomy is that astronomers like to generalize chemistry a lot. Anything that isn't hydrogen or helium is considered a metal by an astronomer. It has to do with kind of the things I talked about last week with how gases fuse in the centers of stars. Things that aren't hydrogen and helium behave very differently when you're dealing with those kind of processes. They can trap atmospheres like Earth, but that's not a requirement. And in some cases, they have trapped atmospheres and then they lose them later in life. For example, Mercury, we think had an atmosphere, but over time, the high radiation from its proximity to the sun kind of forced that atmosphere away. The other type is gas giants. Those are planets like Jupiter and Saturn that are just kind of big balls of gas. This is where the definition kind of breaks down, because when the planets get big enough, they start to look like really small stars and less like really big planets. And that especially happens when you start dealing with those brown dwarfs I alluded to last time we met. Chris actually mentioned to me before this meeting that his research group, someone in it is doing research on how to define those two things, how to kind of differentiate between what is a really, really big planet and what is a really, really small star, because in the context of astronomy, they look really similar. They typically form outside of what's called the frost line, and it's basically just a distance away from a star where gases that are normally gas can start to condense and freeze into ices, and when they do, they start to collect and form giant planets. And as I mentioned, they kind of butt up against, when you get to really high mass, they start to kind of look like stars and less like planets. And that's, again, one of these weird area of debates. So planets are really easy to understand when they look like us and the things around us. When they get really small or really big, we start to not know what to do with them. So kind of another thing to think about is that we're not alone, quote unquote. Other stars generate planets in the same way we do. Granted, they typically have fewer planets, we think. There's a lot of things we don't really understand about why the solar system looks the way it does as compared to other systems we're able to observe. There's a few events that we think went down in the history of its formation that allowed for not only so many planets, but planets that are placed in the ways that they are, which are kind of unique to our solar system. Someone's trying to join, it look like. there's actually a few ways we can see planets. That first way I showed you at the top, that's called direct detection. It's the hardest way to observe planets because admittedly planets are really small and they don't typically give off a lot of light. So we got lucky with this observation. I don't remember the system offhand that this is, but there were a few very bright planets spaced enough from their stars that it was observable, and a star that was close enough to us that we could observe them. The next kind of most simple to understand is called transit. That occurs when a planet passes in front of its star. So if you think of like a solar eclipse, when the moon passes in front of the sun, we can learn some things about the moon from that happening, like that it exists or how often it passes in front of the sun. In this case, what we're really looking for is when a planet that's orbiting a star passes in front of the sun. So if you think like when we made all those observations about Mercury's transit or whatever, that's essentially what we're doing. We're just looking at other stars than the sun. The last, and it's a little bit more complicated, and that's why I kind of provide the diagram. If you know a little bit about physics, there's something called the Doppler effect. When an object is moving, it causes the wavelength of things it's transmitting to change. So when you think of like an ambulance driving by, it sounds high pitched when it's coming towards you and low pitched when it's going away. It's because its movement is changing the wavelength of the sound it's emitting. And so when it's moving away, it stretches it out, it makes it lower frequency and therefore lower pitch. When it's moving towards you, it does the same thing, but compresses it, making it higher pitch. Doppler shifting occurs when stars do that with their light. So when a star is moving away from you, it stretches the light and it makes it look redder. And when it's moving towards you, it compresses the light and makes it look bluer. And if you have a sufficiently heavy planet, it causes the star to kind of wobble in place. And by observing how the star wobbles, we can get an idea of how massive that planet is, as well as some qualities of its orbit. And so these are kind of the quick list on things that we're interested about planets. So first would be the radius of the planet, as well as the mass. And those are both important because they can also teach us a little bit about density. And density is an important step in understanding what the planet is made of. So we find that planets of a certain density are typically terrestrial, other densities are typically gas. I think Chris has a little write-up that he just sent kind of talking, expanding on what I was saying. Next thing is semi-major axis. That's a fancy word for how far away from the star it orbits. We use it because of the fact that planet orbits aren't circular, they're ellipses. And so calling it radius is kind of wrong. But in most cases, they're close enough to circles that the difference doesn't matter anyway. So either of those terms are okay, but the scientific one would be semi-major axis.
So I have a question.
Yeah, what's up?
Yeah, so I'm reading what Chris just said. So you said that it is very difficult for most detection methods to find Earth-like planets or small terrestrial planets. So I'm assuming compared to gas planets.
Yeah, and that's why when I said there are like 3 planets in each system, you're right. Your intuition is true that being big, being massive makes you way easier to observe. So things that are small are hard to observe. Gas giants are easy. Terrestrial are hard. The reason I say 3 maybe is because we think maybe some selection bias is coming into play, as I think Chris mentioned. And so we don't really know that that is true. We just think it's true because it's what we can observe. And so there's kind of a whole field of planetary science and figuring out what those abundances are and how we can kind of tailor our observations to those. Another thing we can get is equilibrium temperature. That's actually something I'm going to talk about a little bit later because it's what I did my research in for the past year or so. Atmosphere composition is also important. Knowing whether there's oxygen present in a terrestrial planet's atmosphere that is about as far away from its star as Earth is from our star could teach us a lot about the possibility for life existing on that planet. Planet structure and planet radiation also are important. When I say planet radiation, I'm actually referring to light the planet itself emits versus light emitted onto it by its star. Structure it kind of goes back to like the radius, mass, density type stuff. Knowing whether it's a gas giant or terrestrial is important because it helps us fill in the bubbles of when these things kind of appear. And then the next step after atmosphere composition, and it's a little bit more technical, is whether or not there are clouds on the planet. We can kind of learn that from, and a lot of these things we only learn from those methods I mentioned before. Atmosphere composition and stuff, it's really helpful for us to get transits because then we can see what kind of light the atmosphere is blocking. And that also tells us about cloud presence. If the light can get pretty deep in the atmosphere, we know there aren't clouds until pretty deep in the atmosphere. So now I'm going to kind of transition over to the other side of what I mentioned at the top, which is talking about astrobiology. This guy on the left here is Enrico Fermi. You might have heard his name before, but he's typically kind of talked about mostly in the fields of nuclear physics versus astronomy. He's known most for working on the Manhattan Project when we were doing that in America, as well as being the inventor of the first nuclear power plant. So he has some acclaim in the physics field, but he did a little bit of work in kind of this side field of astronomy while he was still alive. And so the Fermi Paradox is something that was named after him because it followed from some things that he had kind of thought about while he was doing astrobiology, which is that we believe there are billions of stars like our sun in the galaxy, and it's very likely that some number of these stars host Earth-sized planets at distances away from their stars as the Earth is from their sun. So we think that there should be a good number of planets in our galaxy that host Earth-like, or good number of stars in our galaxy that host Earth-like planets. A lot of these stars are far older than the sun, which means that their planets are probably also far older than the Earth. And so we would figure that because of their age as compared to ours, they would have had plenty of time to develop the same evolutionary processes that Earth did. And so assuming that there isn't some higher power or some asteroid that hit Earth with life on it or some other strange oddity, we believe that these old planets should be able to have intelligent life at the level of or above the level of intelligence on Earth. And from that line of thinking, even if like 1% of the stars have Earth-like planets and 1% of those planets are in conditions to produce life and 1% of life becomes as smart as humans, we think we should have heard something by now and we haven't. And so that's the Fermi paradox. The fact that even if we're giving the most conservative estimates for how much life there should be in our galaxy, we're still coming up empty on anybody trying to, any other alien life trying to communicate with us. So that kind of led into this field of astrobiology and SETI, which is the search for extraterrestrial life. One, the aliens are not in Area 51. The CIA released a bunch of papers fairly recently about what Area 51 actually was. But we have a few guesses as to why maybe there isn't intelligent life that's trying to communicate with us. The first is this idea of a great filter. As a lot of us kind of know, we live on a planet with finite resources, and at some point we will use through them. If it is impossible for a species to settle on another planet or prevent the complete use of their own planet, then we believe that maybe one of the reasons we don't see intelligent life is because simply by being intelligent life like humans, you run your planet dry of resources and die. The next is that intelligent life, even on Earth, is extremely uncommon. When we look around us, every other animal is at the same state in their evolution. They've all had the same time to become as fit as they are on the planet, but only one species seems to be as smart as we are. So expanding that out to other planets, it would hold to reason there might be space dogs running around somewhere, but space dogs aren't smart enough to send radio waves out into space to try and find other living things. The last is maybe there is something just kind of existentially special about the Earth that allows for us to have life, and we just don't know what that is. But we do have some people that are looking for them. And on the right there is a poster for a movie, Contact. It's about SETI, the search for extraterrestrial life. One of the things we do is just kind of watch for radio waves or other kind of light coming from planets that doesn't look the same as light we expect to come from the planet, some sort of signal possibly. The next thing we kind of do is look at our own planets. You probably hear a lot about trying to find bacteria on Mars. If there's evidence that even in our own solar system, it's possible for there to be unintelligent life, it seems very, very likely that there should be some form of intelligent life somewhere else. The last, and Chris knows a little bit about this more, but it's Carl Sagan's search for life on Earth. And it was, to my memory, this experiment that was conducted by a group of scientists to kind of utilize the same methods we use to observe other planets on Earth and see if we would be visible. And it is, while technical, a pretty good read because it goes through a lot of interesting questions we have to ask. Because one thing they point out in kind of their headline thing is if you point a telescope at the day side of Earth, other than the fact that the surface of the Earth is fairly green, which could be explained by plenty of other things, you can't really tell that there's anything living on the surface. It just looks like a planet that is there. And so if you had huge iron deposits or copper deposits that had rusted over green, it would look the same as the presence of life on a planet. So this study kind of answers and asks some interesting questions about how we go about looking for aliens. I kind of wanted to touch on was my personal research, which doesn't have to do with aliens. I specifically study gas giants called hot Jupiters. They're planets that are really close to their stars, closer than Mercury is to our sun, but have radii masses like that of Jupiter. We find that typically they formed kind of where Jupiter is, but over time gradually move inward towards their stars. And what we see is that when we get them hot enough, when we kind of blast them with enough, if we kind of blast them with enough radiation from their star, the outer layers kind of puff up. I didn't do it justice. Chris has just read it in the last month or two, so he can definitely talk more about it if you have questions. It also isn't my area of research. I'm dealing with hot Jupiters, which are completely different. We notice that they seem to kind of get bigger than we expect. And we think that maybe something is going on the outer layers of this planet, whether it's a chemical change, something to do with cloud formation, some other process that is causing the planets to trap additional heat and then expand a little bit because more energy means you can resist gravity more effectively and then be bigger. We also think maybe it's just some product, some artifact of how gravity interacts with the planet when it's that close to a star, kind of stretches it out a little bit. So my research didn't come to any great conclusions, but what I found was that, yeah, there's definitely a relationship here between how much light a planet receives from its host and how much, what the radius of that planet is. So I'm kind of wrapping up here. Chris, if you want to give a better rundown of that paper than I did, have at it. I haven't read it in a long time.
Yeah, this is dope, man. Thank you.
Oh, I was actually typing in the chat, but I guess I can just speak on it. Basically, they were able to detect oxygen, which is, obviously is actually a pretty good indicator of life because oxygen is pretty unstable, and so if you find it in large amounts, it doesn't guarantee that there's life, but it's indicating that something's going on, which could be a biological process. They had evidence for chlorophyll/photosynthesis. They were able to map out the forests, oceans, and clouds on Earth. This is all just using light. And they could even detect clear radio signals, which would indicate potentially intelligent life. And granted, we know that there's life on Earth. So the whole thing might seem kind of, I don't know, why are we doing this? But it kind of gives us a baseline comparison in terms of what we might find on another planet if it did have life on it and what that would look like. It also reveals how much information we're able to get from an exoplanet just by looking at the light that it emanates. And you're able to fully map out the land and the oceans, and I think that's like super cool. But yeah.
And another thing is, like, obviously we're much closer to Earth than we could be to any other planet, and knew what we were looking for. But it was also written by Carl Sagan, who, while he was an amazing scientist, was really kind of more interested in taking apart the process of science than doing science for the sake of science. And that's why a paper that is more exploratory of the methods is something that he wrote versus simply direct science of how we're observing other planets.
So you pretty much you're saying he liked to write books about it, but he liked to speculate because it sounds good, but the actual data, is that what you mean?
Well, yeah, because of his kind of fame as a scientist, he took on a role where he was more looking at science he was more researching science than researching the planet itself, right? He was more kind of being critical of how we observe these other planets, maybe not critical, but being kind of introspective and thinking a lot about how we observe those other planets than literally doing science to discover whether there's life on Earth, right? Because we know that there's life on Earth. That's not a question that we really needed answered.
Got it.
Great. Are there any other questions? I would recommend the movie Contact. It's a pretty good movie about the search for extraterrestrial life. It does it pretty good justice. It's a little bit dated, and some of the things about it are science fiction versus science. So
yeah,
any science fiction movie, you have to suspend some disbelief at times.
Yep. And then Will and Jalen said they had to go to Fate, but they said they appreciate the presentation. So that's why they had to go. But you can continue.
No, great. So yeah, that was pretty much it for what I had. So unless there are any other questions.
Cool. We got a new brother, man, Tyran. Tyran, you there? Can you hear us?
Yeah.
All right. So Tyran, man, any questions you have for Dante? Please go ahead.
How did Pluto come out missing? And he should have been in planet that stayed with the rest.
Sorry, what was that? My audio cut out for a second.
Could you repeat that again, Tyran?
How did Pluto be the planet that gets out the solar system and Pluto could stay in?
So the planets that aren't in our solar system, I think I'm understanding what you're asking. They're in other stellar systems, not solar systems, because it's not the sun. Pluto we just exclude because it looks different from all of the other planets in our own system enough that we don't think it's useful to keep it in the same category. It looks kind of similar, but again, it is a rocky planet that's further out than we think they should form. It doesn't have a nice circular path on the same kind of flat plane. And the reason that is just how it formed. It got kind of gravitationally thrown out by other planets in the solar system. And with that, we kind of just say, yeah, it's not similar to other planets we observe in our system. It looks a little bit like maybe stuff we might see elsewhere, but it's definitely not similar enough to like Earth, Mercury, Venus to be considered the same. And the reason it's not on that same plane, which is kind of one of the big reasons we don't like calling it a planet, is because during its formation, especially since it was kind of one of those Kuiper belt objects and not a planet, it got gravitationally tipped out of its path when typically we would expect everything to form on a flat level. And that's just something we're still trying to research and don't fully understand, because we think everything should stay on a flat plane, but we know for a fact that a lot of things don't.
Cool. I didn't know that. Cool.
Yeah.
Good question, Tyran.
Yeah.
Yeah. So Chris, hopefully, you definitely love the chemistry. We really appreciate what you all are doing. Again, like I use these videos and I just give them to my students and I have them do assignments for them. They really appreciate it as well. So, just come in here, and just give us your, expertise, because it's really appreciated.
Right. Yeah. And sadly, this is probably my last meeting for now with you. Again, I think I might have mentioned a couple weeks ago, I'm looking to fill the role of the Michigan College Advising Corps student that you had there. So I might be coming back. I might not. They might put me somewhere else in the state. So we're still kind of figuring that out.
Yeah, man. We love to have you, man. So please keep us updated on that.
Absolutely.
Absolutely. Yeah, I know, right? Isn't that so cool, Valencia? Absolutely. Cool. Chris, do you have any questions for us, man? Is it Chris or Christopher? I know I know your name is Christopher.
I don't really care. Most people call me Chris.
All right, cool.
But no, I mean, I think Dante will probably just explain to me like the specifics.
Yeah.
You know,
I have to learn a
me
little bit
and like,
more.
and I should be able to get other people from SAS to also help with this, so it's it won't just be me.
Yeah, absolutely, brother, man. Because we know you all are out of school pretty much, and so whatever you can, we really appreciate it. So the more, the merrier. Thank you.
Right. Well then, yeah.
Absolutely, cool. Yeah, so Dante, please just send me the link whenever you can, and then I look forward to seeing you all next week.
Absolutely, yeah. Thank you so much for having me. It was a great experience. I'm glad I got to meet you guys. Hopefully, I'm hanging around in your school a little bit. So.
Yeah, bro.
Or not a little bit, a lot of it, 5 days a week.
Yeah, man. Imagine what it's like virtually, in person, man. If it's like this virtually, we can do some cool stuff in person. So yeah, thank you all. Thank you, Chris. Thank you, Valencia. Thank you, Tyran, for coming. I'm gonna see y'all later, okay?
Yeah.
All right, y'all take it easy. Bye-bye.